Hello everyone. So welcome to the next week of this course. So what we have been discussing in recent lectures have been how to generate energy in a clean manner, and what we have seen is that electricity is going to play a major role in this. And while we have been discussing electricity, we have been also discussing about that could be the major sources for electricity generation, which could lead to a low carbon footprint energy generation, what has been challenges in that, and in that taking over those challenges or solving those challenges, we have now reached, we were discussing that how storage can play a major role in this, and that is what we were discussing in last couple of lectures. So, let us continue our discussion on storage, because that is kind of becoming the key aspect in all this journey of renewable energy transition. And what we had discussed so far was general in terms of need of storage. We had discussed about that what kind of technologies are there in storage. And now let us move to a technology which is probably the most talked about technology in storage in current days, is about the battery storage. So, I just touched upon battery storage in my last lecture, did not go deeper into that. So, let me start picking up from there. So, battery storage, if you look at it, is the fastest growing energy technology globally of late. And I shown you through some data that though the pumped hydro storage has been the main source of energy generation so far, what is projected or what is anticipated is that battery generation or battery technology itself is going to overtake that, or is going to be the fastest growing thing all over the globe. And in that specifically, what we were seeing when we kind of met last time was that already 41 gigawatt of battery storage has already been deployed in 2023, and in 2024 this number would have also gone up. So, that has really kind of taken off late. And if you look at it, the journey really started around 2020, which is almost nothing, from 5 gigawatt almost to about 40 gigawatt, and this growth is exponential, and this growth is going to grow faster and faster. That is how it is anticipated. And when we talk about battery, always we talk in terms of the mobile batteries, or we talk in terms of some consumer driven batteries in terms of pencil cells or mobile battery packs and all those things. But as you can imagine, those batteries are smaller batteries. So, even if you multiply thousands of them, the kind of deployment of battery which is taking in energy domain, specifically for the grid connected, is probably the biggest user of this utility scale deployment is becoming bigger and bigger. Though electrical vehicle number is looking very big out here, but the current numbers which are showing is that in terms of the actual number of deployment, the energy scale utility is growing very fast. So, that is what is happening. And if you start looking deeper into these numbers, so if you already installed capacity storage wise, if you look at it, and if you look at it in terms of projection, so just from 23 to 24, the moment, as we already discussed with this one data, that pumped storage has kind of remained stagnant, but battery storage at utility scale, especially for energy things, has grown up drastically, and behind the meter uses also has gone up. And if you then start looking deeper into the numbers in terms of projection, both in terms of stated policy numbers as well as net zero numbers, what you basically see is that pumped storage, while it will have its own journey, major path of the growth would come from the batteries, and this will be both utility scale batteries as well as behind the meter batteries. Behind the means like home uses and stuff like that. So, those kind of batteries will also have their own role to play, but it is primarily the growth with the utility scale batteries which will kind of drive the whole thing. So, you can imagine that what does utility scale batteries means? Basically, deploying batteries with renewable energy generation sources, be it solar, be it wind, be it any other renewable energy generation technology, where basically what we are saying is the battery will play a role in terms of the storage of energy from those resources, and to be utilized from an energy balancing perspective, from transmission balancing perspective. And we talked about all this wherever the battery would be needed, and from all that we would be then seeing that this whole transition of the storage, from which just a single dependence on pumped hydro storage, that will move to more and more battery storage dependence. And so, that is what is going to be the key going forward. So, what is expected is that it will get driven by renewable energy integration, declining cost, electrical mobility ecosystem, that will also drive a lot of things. And so, if you start looking at numbers recently, so if you see that the deployment which is also happening, because of that the cost has started to come down drastically. So, there is a rapid growth almost on year basis in terms of the net cost, both at the pack level as well as the cell level. So, Just the cell price is the major price which kind of drives the battery cost. So that is also decreasing continuously, and on top of it some addition to pack cost also comes, but pack also has declined drastically. So barring maybe 2022 as an exceptional year because of the after effects of COVID, but beyond that almost year on year there is a drop, and it is expected to go down much faster as we kind of go along. If you look at more in terms of mathematics, these numbers are much higher compared to the renewable energy source itself. Like if you compare these numbers to say suppose solar or wind, these numbers would be higher, but you don't need battery for all the time, and we will look into this, that why does storage doesn't put so much of cost burden on the whole system. But as you can see that storage itself is the battery per se, the cost is declining year on year. The growth is almost across the world in terms of the how the deployment is taking place, how much battery storage additions are taking place worldwide. Again, China is leading the race, and United States is also, United States and Europe also is kind of catching up to it. India is still not there in the main race yet, but the way things are going in India, and which we already discussed in terms of when we were discussing solar and wind, you could see that India is going to be a major part of this race as we kind of go along. But overall the message is very clear that the battery storage is growing very quickly, and this is going to be the one of the major storage technology as we kind of move along, right. So now let us understand slightly bit more on the battery energy storage system. These are basically, they store the energy in chemical form and then they release it whenever is required. They operate through basically a electrochemical reversible technology. I am not going to technology at all in this lecture, so let us not talk much in terms of technology. The major chemistry or major material which is used for storage these days is lithium ion technology. So we started our journey with lead acid, then we were talk about nickel cadmium, and many other chemistries has been kind of discussed during this battery journey. Currently the most used or most talked about molecule which is used for this generation is lithium ion batteries. And so we though it be mobile phones also, or be it be car, or be it maybe utility scale also. So most of the batteries are lithium ion. So in that also multiple things can come. It could be polymer based, it could be liquid based, it could be lithium metal based, or it could be lithium ion based. So it could be multiple technologies which are there, which is kind of driving it, but nonetheless they are primarily lithium based. Many new battery chemistries are being discussed these days, like sodium is another thing which is being talked about, aluminum is another material which is talked about. People are talking about metal air batteries also, which could have higher energy density. So a lot of research is going around in the world right now around this area, but overall this field is really growing. What it can be used for is basically from a storage perspective, as you will remember earlier, what we discussed was that this can primarily be used for a few hours of storage. So it is usually during the between minutes to days kind of that kind of a time frame. So this technology is basically filling the gap between the very short storages that we were doing in terms of using flywheels, or maybe very long storages that we can do using hydrogen or pumped hydro storage or technologies like that. So there is kind of a bridge between the two things, and since the maximum uses from a renewable energy generation would actually come between the same day kind of a storage, and what you need is something to react much quickly. So that is where this technology becomes very handy for that specific uses. In terms of the overall storage landscape, as we were discussing in the last slide, that the storage landscape can differ by discharge duration system role. We have looked this graph earlier, but especially talk in terms of batteries. So they basically are used for energy shifting purpose. So what you can do is that you can generate the solar power in the daytime, and you can use it for evening demand. You can use it for peak load management. You can use it for grid balancing, and this is where the kind of batteries are kind of lying in this domain. That's what we were discussing in terms of discharging time. So and also in terms of storage capacity also, they kind of lie between here itself, because otherwise the cost may become very expensive. So this is the battery bracket that as you can see, that in terms of time frame, this is the kind of time frame that we are talking about in terms of few hours to maybe a day or so, something like that. So that's where they kind of, this is used a lot, and this kind of almost fills up the gap between this very high storage using hydrogen and everything like that, and or the very low storage in terms of supercapacitor. There are other technologies also, but they will have their own scale up issues. See, one of the biggest advantage of battery, which as many of you would know and you can understand, is that it's a very modular technology. So you can have a battery pack of maybe a couple of kilowatt hours or maybe a couple of kilowatts, and that could actually be multiplied to convert into a megawatt facility. And so that's kind of a very flexible kind of a approach which a battery technology can give. Like imagine a hydrogen source. Like once you have made a tank, to have the tank used at the full efficiency, you need to have a minimum kind of storage in that, and there is a maximum thing that you can store in a hydrogen tank. Similarly for compressed air, similarly for pumped hydro storage also, that there is a water reservoir size which is available, and now for you to have maximum efficiency, so you cannot run it using a very low level of water, and you cannot go beyond a certain height in terms of water before the water starts to spill out. So and if you need to really enhance the facility afterwards, you need to have another multiplication. So that way battery kind of gives you very kind of a good scale up possibility also, and it's kind of in between the very long storage and very short duration of storage. But having said that, it is not useful for long duration or seasonal storage because it is the own internal losses. So this will have a role in between the whole thing, it will kind of play. Another advantage of battery storage is that it has fast response time, so it can really be used for frequency regulation or grid stability. It has very high round trip efficiency of about typically 85 to 95%. It could be modular and scalable across applications, as I already talked about. So like it could be multiple cells which could be stacked together and it could be used. So you can use it for co-locate it along with the RE for each province to put in the right electricity in the grid at the right amount of time, not overburdening the grid with sudden generation and then no generation. So you can really flatten this curve out, and then you can have a longer pumping to the grid for longer duration. For grid connected batteries, you could have it the kind of, you can then use a grid, whatever power is pumped into grid. If you have variation on the demand side, you can really store the energy in the batteries, and then you can pull back that this energy back as per your need. And then from a demand side perspective, this is a behind the meter thing. Once you get the energy here, and suppose you can get energy cheaper in certain duration, you can store that energy in batteries, and then you can reuse it whenever you want to use it. So application could be along the utility scale, it could be on commercial or industrial uses, residential uses. So overall, it kind of gives you a lot of flexibility around across the value chain in terms of battery usage itself. Okay, so that kind of sums up that what kind of various technologies that we have in this energy storage journey. So we have talked about multiple technologies, we have talked about pumped hydro storage, we have talked about compressed air, we have talked about batteries. We have not talked so much about flow batteries, but that is another thing, that just a variant of battery technology, flywheels, capacitor. So we have talked about multiple aspects, but all of them will have their own challenges, all of them will have their own nuances when it comes to deployment. And as we have seen that, one, the storage capacity of these technologies can vary from technology to technology, storage duration can vary, and similarly the cost itself can vary across the technologies, and some technologies will have higher initial cost and then lower ramp up cost. Some technologies will have a high initial cost and high and lower maintenance cost. Some technologies will have a kind of a more modular kind of a cost across the value chain. So it will all really depend upon that which kind of application that you are talking about. So overall, if you start looking at the energy storage technologies, like batteries will have its own concerns with respect to lithium and cobalt value chain issues. They will have some environmental and recycling issues. There could be economic challenges because it will have depending upon the design. So overall, not only battery, but any other storage technology will not be a universal one fit all solution. It will all depend upon that kind of end solution you need to have, and depending upon that end solution, you will have the right fit of the technology, which will then go and fit in the final picture that will fit into. Like I'll just quickly touch upon it. Like when we were talking about batteries, I just wanted to complete this picture. So I had discussed about these things in detail in solar and wind, but since this is not a battery lecture, this is more of an energy storage lecture. So just to kind of give you a quick glance of in terms of global battery supply chain issues, is that there are manufacturing concentration challenges in this technology also. Again, China is playing a similar role at all levels, be it mining, be it material processing, be it cell components, be it battery cells. Especially as we go along down the value chain, you can see the dependence on China increasing and increasing. So since China is becoming manufacturing hub of the world, so specifically at a cell level, almost all the manufacturing capacity is again getting concentrated in one country. So when we are talking batteries, so the another challenge which this technology can bring is that, will we have the same dependence like solar or wind? Will we have the same kind of a bottleneck coming for batteries also? So that's another cause of concern at the back of the envelope, and which you guys should know when you are thinking of this from a long term deployment perspective. But okay, so then we start summing up the overall storage technology perspective, is that you will have a storage technology which will then depend upon the uses. So, depending upon uses, for very short duration you can have supercapacitor, flywheels and everything. Mid thing would be something like batteries, and the high thing would be simply like pumped hydro storage or compressed air possibilities. And so, just to repeat myself, no single storage technology will have a kind of a meet all requirement, and then that's where you need to keep in mind. So, whenever you either you are a policy maker, or you are a energy engineer, or you are working on this from a pure tech perspective, what application are you targeting? So, when world is looking for this transition from fossil fuel based dependent energy generation to non fossil fuel based energy generation, it is not one energy technology which will play the role. As researchers in this area, as policymakers in this area, will have to then bring out the right specs for the right uses, for the end uses, in terms of what needs to be used and how that needs to be used for that specific application. And that is a very critical thing from a cost optimization and from a utilization perspective also. So, that's a kind of a thing which needs to be kept in mind for all this deployment. And when we are doing that, we need to keep in mind for a lot of performance characteristics of the storage system. What matters is how much is the round trip efficiency that you are targeting, and what is the energy density that you are targeting, because energy density will lead to what's the space that this specific technology will kind of have. For example, if you look at in terms of comparing the pumped hydro storage to a battery, the energy density of pumped hydro storage will be much lesser compared to the battery. So, that will have its own challenges with respect to, if you really want to put in a lot of energy into one specific concentrated area, that could be challenging. There could be storage duration challenges also, like some technologies will have a storage duration with respect to hours and months, to minutes, days, to maybe seconds also. So, it will all depend upon that what you are trying to look for, because then it will kind of lead to that what kind of capital cost that you are looking for. So, for example, if you are really looking for months and hours, the initial capital cost is very high, while you are looking into from a very short duration, the capital cost becomes low. So, it will all depend upon that what are you trying to achieve and how you are trying to kind of look into the picture. What you should also keep in mind is what is the cycle time, what is the self discharge rate also. Self discharge rate also becomes very critical, because self discharge rate will kind of determine that can you hold the energy in that specific source of energy storage for how long period, because that will kind of determine that for how long can you use it. So, it is a self discharge can also be a bottleneck for many of these technologies. Like for example, when pumped hydro storage, the self discharge is very small, while for a flywheel the self discharge can be almost 100%. So, basically depend upon that how much of self discharge would you want to allow. So, there are multiple characteristics which you will need to keep in mind while selecting energy storage technology. And so, that kind of gives you multiple constraints that we have talked about, that we have talked constraint in terms of size, we have talked constraint in terms of charging discharging period, we have talked constraint in form of that for what uses you are trying to use it for, what kind of energy density you are looking for, what kind of cycle life that you are looking for. So, this kind of it determines, it's not a one fit all solution, again just to repeat myself, but you have to understand as policymakers, as students, in terms of where do you go and how do you kind of use the right technology for the right uses. Okay. So, one more technical term which I want you to understand if you are trying to generate this any strategy around this in terms of overall energy storage, is that we usually have talk in terms of two specifications. We talk in terms of power capacity, which is in kilowatt, megawatt or gigawatt, or we talk in terms of energy capacity. So, power capacity is that maximum rate at which the electricity can be delivered. So, it is basically how much power the source can deliver is at what rate. So, basically it is energy per hour. How much energy can the source deliver per hour or per unit of time. So, how much of energy, at what rate can this energy be delivered, that is given by power rating. So, you always talk in terms of two ratings. You talk in terms of that how much energy you have available with you, which is given in form of kilowatt hour, megawatt hour or gigawatt hour. So, basically you can say that if I want to use this energy, how many of gigawatt is available to me for how many hours. For example, suppose you are putting up a solar cell facility. So, you are putting a solar cell facility for 1 gigawatt, for example, and then you can potentially generate, for if the sun is coming for 5 hours, you can potentially generate 5 gigawatt hours. And if your uses are is only for maybe in the during that 5 hours, you can potentially use only 0.5 gigawatt on an average basis for all those 5 hours. So, basically what you use is that you use 2.5 gigawatt hours of energy, is that what you have consumed during that period. Now, since you have consumed 2.5 gigawatt hour of energy in that period, while you have generated 5 gigawatt hour, so effectively you can go and save that 5 gigawatt hour of energy. That will be your bank, that will be your kitty. And now from that bank or from that kitty, how much of power you want to draw and deliver per hour basis is what is basically determined by the rate at which you can delivering the energy. And so, then need to be cognizant of both the factors together. You need to be aware of that what is my total size of storage which is available, at what rate then I am consuming it. So, that will determine that for how long can I use that resource. So, it kind of power capacity basically determines that how much is the supply can be given at that specific moment, and energy capacity basically then determines that how long the storage system can operate depending upon the rate at which you are delivering the power. So, when you are trying to deliver something, when you are trying to store something, you basically need to worry about both with respect to capacity and what is the discharge. So, same capacity, if you are discharging faster, then it will kind of drop faster, and for same capacity if you are discharging slower, then it can deliver the power for a longer period of time. So, you need to keep in mind when we do that storage sizing, we always keep in mind both with respect to power capacity as well as with respect to energy capacity. Then you can see that basically duration depends upon that what is my energy capacity depending upon by what is the power capacity that I am working for. For example, suppose we have a 400 megawatt hour capacity. So, our storage duration with 100 megawatt battery is about 4 hours. So, this means this system can deliver 100 megawatt for 4 hours, or the same system if I then, so suppose the energy capacity in this case is 400 megawatt hour. Suppose I am drawing 100 megawatt on an hourly basis, then effectively I have a source which is available for 4 hours. But if I then do not draw 100 megawatt, if I just draw 50 megawatt of power from that, from the same source, then I can get my electricity for 8 hours. So, that is the kind of difference that will come, and that will also determine that for how much uses which I am designing the system for. So, I need to know both the energy capacity as well as the power capacity. And so, power capacity basically limits me that how quickly can I draw the power, or how slow can I draw the power. This will all depend upon my transmission system. This will all depend upon that what kind of system do I have in terms of load balancing and in terms of delivery system. It will depend upon the efficiency of overall the delivery system, while the energy banking will depend upon that what kind of storage medium do I have, and how long can it hold on to that storage and stuff like that. So, but usually when we determine the cost, we usually determine the cost in terms of dollar per kilowatt hour as a major uses. We always look into dollar per kilowatt also, but dollar per kilowatt hour is the major uses. And just to give you an analogy, when we buy our mobile batteries, or whenever we buy always in mAh or watt hours, or like that is how it comes, because that is the basically it is the energy capacity component which dominates the system cost. A longer duration storage requires more battery cells. I am talking in terms of batteries, but you can imagine this will in form of all the storage technology which is available. But when we kind of then go into taking out power from this, as I already mentioned, it will depend upon what kind of inverters do I have, what kind of power electronics do I have, what is the grid connection do I have. So, from a storage perspective, this determines kind of a storage, this kind of determines my delivery system. There are two things that you need to kind of worry about. So, if you really want to do at a system level, you will need to know both power capacity and energy capacity, but you have to talk in terms of storage cost itself, then you basically need to talk about in terms of energy storage. So, that is how you kind of work out with respect to overall costing mechanism, and then this knowledge will kind of help you to see that how to rate your energy system rightfully, right. So, just to give a quick comparison in terms of the whole thing, let us compare the two technologies, pumped hydro storage and the batteries. So, pumped hydro storage will have low cost and large scale. So, if you talk in terms of the overall system, so it can have very large capacity, right, but it can have a slow deliveries, right. So, it will get determined by that, but on the other hand, batteries can have medium kind of storage, but it can have fast delivery. So that kind of difference, and that's what you kind of work out in terms of how to design your system accordingly. Another comparison in terms of pumped hydro storage is that it is a low cost at a large scale. So basically pumped hydro storage, the system cost kind of goes up. That initial cost is usually very high because you need to have all the infrastructure to create those ponds and to create that infrastructure, but then the ramp up speed is slower. So at a certain capacity, the net cost per kilowatt hour, so dollar per kilowatt hour will be lower here. While in case of battery, what will happen is that initial cost though will be higher, but since the battery net cost is high, so for the same kind of a energy requirement, the dollar per kilowatt hour usually, at least with the current technology, is usually on the higher side. So but as you can see that initial cost is lower in case of battery. So if you are looking for a system flexibility perspective, if you are looking for a medium storage for a medium duration, that's where the batteries will come more into play. So pumped hydro storage will give the cost advantage at scale, and battery will give flexibility and modularity to the system. So this could be a combination of two things, and this could be really how do you really want to design your system. So that's how the old nuances of this storage system comes into play, and that's how you kind of can move towards that, what to choose for what application and how to kind of deploy it rightly. That will kind of become the key in this. Moving on to India, for India also the energy storage requirements are becoming large, more and more, as we have talked that India is taking this very aggressive target in terms of this renewable energy generation. So large scale solar expansion is expected. There is an issue of evening peak demand management with respect to this solar generation, because then solar energy is getting generated during the daytime while that is not being consumed during the daytime. So what you can potentially do is that you can store this energy to be used at the evening time, or let me not talk this right now, but as you can see that whatever energy that you are generating extra here, that you can potentially use it for this uses or for this uses, depending upon where you want to use this energy for. This specific thing will come into picture, that suppose your rate of electricity are lower in the evening time or during the midnight period, then you can probably store energy here, and you can also use it to meet your evening peak strategy also. So for India, the demand would primarily come in terms of extra generation which is happening because of solar, or maybe in some cases wind, and use it maybe in few hours a time frame is where the maximum uses will come. So basically this whole demand of India's grid balancing will come between 4 to 8 hours kind of storage, and that's why many tenders that you are seeing in India of late are coming of that order, that where 4 to 8 hours of storage is what is given as a requirement for this energy storage system. Basically this is, as I have already talked about, this is being driven by growth of hybrid renewable and storage system, and this is leading to increasing adoption of battery storage. Pumped hydro storage systems are also going up. As you can see that from a storage perspective, multiple technologies are being talked, and so India is trying to kind of work around all these aspects. A lot of policy level interventions also coming in India. So the national framework for energy storage system was put into frame 2023, and I already discussed some of these numbers, so I am not repeating that. A lot of tenders these days is coming with a lot of storage requirement more and more, and it is getting more and more integrated into power system planning. The storage is becoming kind of a mandatory part of it. The whole energy transition planning model for India, and we have talked about some of these numbers, so I am not going to repeat those numbers. And this procurement is primarily led by SECI. So SECI, most of the SECI tenders these days is kind of coming with this kind of a round the clock deployment and things like that, which I have already talked in terms of when we talk about solar wind hybrid with the storage possibilities around it. If you look at the outlook for energy storage in India, it is expected to play a major role as we kind of move along. And though India, as we saw earlier, there was not kind of figuring out or not getting kind of cannot be seen to be the most aggressive player in storage so far, but this is expected to play, as India is going to be one of the major forces in terms of renewable energy deployment and generation of renewable energy more and more. Specifically, India has put this very aggressive target of 500 gigawatt of non-fossil power capacity by 2030. So lot, as you can then imagine, that this will be primarily backed by storage as the primary technology to that. If you just look at the expected growth in India, the initial growth which will come again as the word kind of started would be around the both kind of a good balance of pumped hydro storage and battery energy storage system. But slowly, as you can see, that slowly battery will start taking it over, and if you look at some projections in 2047, it will be primarily battery driven storage which will be kind of play the major role over there. That is in terms of gigawatt. So it is about 320 gigawatt and leading to about 2380 gigawatt hour. So in terms almost 8 times. So that's what I said, that the capacity which is being put is being put for almost 4 to 8 hours of kind of storage. So net gigawatt hour which is targeted in India is about 20 to 24 gigawatt hours, which can help you to draw almost 320 gigawatt of power for almost 7 to 8 hours of draw. Is that what India is targeting? So this is kind of a very aggressive path which India is taking for almost nothing. Almost like 16 gigawatt is what is expected to go this financial year, and from there to 320 gigawatt in kind of a requirement, or in terms of the energy capacity, 82 gigawatt is what India is targeting to do this year, which is primarily driven by pumped hydro storage so far. From there, a journey to almost 2,400 gigawatt hour by 2046 is a very aggressive target which India is taking. And but the challenge for India, which will come, is, as you can imagine, which is that India still is not the major manufacturers of these storage technologies. Still, the supply chain dependence will be huge on countries like China. So what India can fear is that India can have a similar repeat of a story what it saw in solar domain, that though India started its journey in solar, if India doesn't start putting its energy storage manufacturing in-house, the whole issue of energy security, whole issue of dependence on imports and dependence on specific geographies for its supply chain will become a key concern for this growth. This growth which is targeted is very aggressive, and for this aggressive growth, it should be backed by the right policies for in-house manufacturing. That is going to be the key for India as we kind of move along. Okay, so that kind of sums up our journey into storage technology. We have already talked about that. Why is storage needed? What are the challenges? What are the various technologies which are available? How does those technology kind of complement each other? They kind of work in tandem with each other. For what application, what can work, and how a policy maker or how a technology maker can choose the right technology for the right deployment during the system design perspective. So both from a policy system design perspective as well as from a technical system design perspective. So but overall this could be a very interesting technology to kind of support this transition. Now let us sum up our understanding for this specific topic. So while battery or storage overall is a very interesting technology to have, it has made a lot of technological progress, but still there are a lot of challenges which kind of remain. One of the biggest one is the very high upfront capital cost. That is a challenge which is there, because so as we have seen that capex cost in this is higher than the renewable energy capex cost. So that is a challenge which these technologies still hold. There is uncertainty in revenue stream, that who will pay for this storage? Will it be generator who will pay for this storage, or it's the end user which will pay for this storage? How will the right cost model evolve? Will the storage technology itself derail the whole deployment of the renewable energy pathways, is a challenge which is still to be solved. However, of late there has been some silver lining in this whole dark cloud thing, because some recent tenders in India specifically, if I can talk about that, is that are coming at a very interesting price of less than 4 rupees per kilowatt hours, of including about 4 hours of storage has recently been tenders, which is a very interesting price number, and which is almost reaching to kind of a grid parity, if we can talk in those terms. So this is the future looks bright from that end, but still there is uncertainty in terms of the overall revenue stream. There are regulatory and uncertainty. Will government continue to support in terms of the overall deployment? Will it have challenges with respect to monetization? Because it's a kind of a complex thing, starting from the generation to transmission to end use. Who is responsible for what? Those kind of policies has to kind of be driven very rightfully. But overall, what you can see, that there is a storage technology is looking as a very bright thing for future. What we can see that we will see a lot of battery driven storage technology which will come. Integration with hydrogen system will also come. Increases the roles of distributed storage which will come. Overall, storage is going to be one of the key things we kind of going forward in this overall journey of our renewable energy based generation system. So in fact, for renewable energy generation, it will require energy integration, will require flexible electricity system, and for this flexibility system would need energy to be stored when we are generating it excess, and use when we require. So there are multiple storage technology, as we have talked about, each suited for different application. Battery storage is currently the fastest growing storage technology worldwide, but there are some critical mineral level challenges in terms of China, or in specifically geographical dependence as well as material dependence, which can derail this path if the world doesn't take a notice of that. I did not go into the social aspects of all that, but as you can imagine, there is a whole social aspect behind all this material requirement, because there has been reports where some of these materials are so scarce and so specific geography dependent that those specific geographies are right now exploited by the storage industry, specifically the battery storage industry. And you might have heard about Congo and cobalt story. So those kind of stories are kind of getting built up in the background. So the world has to kind of worry about that kind of over exploitation. Nonetheless, what we can see is that storage technology specifically is going to be one of the most critical kind of a lever or most critical kind of a support system in all this renewable energy transition. And if it is handled rightly with the right kind of policy framework, with the right kind of financial mechanism, this can really help us to transition towards a carbon neutral kind of a world. So I'll end this energy storage here. I'll look into one more technology, just giving you a quick glance on how hydro and nuclear kind of is supporting in this journey towards fossil fuel based energy transition, before I move to system where we will start looking into carbon capture and whatever carbon is remaining after that. And we'll talk about more, we kind of go along. But in the next lecture, let us meet with nuclear and hydro as a requirement. Nuclear hydro as a need, that what are those technologies capable of doing, and how those technologies can support this transition of journey from fossil fuel based energy generation to non-fossil fuel based energy generation. Thank you.